Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 3 on Taylor series.
In this lesson, we'll harness our understanding of e to the x as a series and extend this perspective to a wider world of functions. This will be done through the key tool of Chapter 1, that of the Taylor series of a function.
In our last lesson, we began with the definition of e to the x as something like a long polynomial. And from that, and a little bit of help from Euler's formula, we observed similar formulae or expressions for the basic trigonometric functions, sine and cosine. Expressions of this form we are going to call series, and we will be working with them throughout this course. The question arises, are there other similar expressions for different functions besides these basic three? The answer is an emphatic yes. We're going to work under the assumption that every reasonable function can be expressed in the form of a series as a constant plus some other constant times x plus a third constant times x squared, etc., for some collection of constants. Now, of course, strictly speaking, this is not true. We need to be careful about what we mean by every and reasonable. For the moment, let's pretend that this is true and see where it gets us. We are first led to the question, how do we figure out or compute these coefficients? The following definition is critical. The Taylor series of a function f at an input 0 is the following series: f at 0 plus the derivative at 0 times x plus 1 over 2 factorial times the second derivative at 0 times x squared, etc. That is, the kth coefficient is equal to the kth derivative of f evaluated at the input 0 and then divided by k factorial. This is a most important definition. And for all intents and purposes, at this point in the course, remarkably, this series returns the value of f at x. Let's see how this plays out in an example that we already know. Starting with our definition of the Taylor series, let's apply it to the function e to the x. In order to compute this, we're going to need to know the derivatives of e to the x, and we're going to have to evaluate them at x equals 0. But since we know that the derivative of e to the x is e to the x, all of these derivatives evaluate to 1. Therefore, when we substitute these values into our formula for the Taylor series, we obtain the familiar series for e to the x. This definition, at least, works in this one context. Let's continue. Let's look at another function for which we know a series expression, that of sine of x. Recall how the derivative of sine goes. That gives you cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine, and then the derivative of minus cosine is sine. Once again, evaluating all of these at an input of 0 gives us alternating forms of 0 and non-zero terms, with the non-zero terms having alternating signs. Therefore, we can substitute in these derivatives, obtaining 0, 1, 0, negative 1, and repeating in blocks of 4. When we write out the resulting Taylor series, we see, once again, the familiar form x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. This is the expression for sine of x. It seems clear that this ought to work in other contexts as well, but let's just check it. For example, if we work with cosine of x, then, well, the derivatives of cosine follow the same pattern as before. Evaluating those to 0 gives us the same numbers as before. Why do we not get the same series? Well, because when we evaluate these derivatives, the sequence of numbers is shifted. F at 0, that is cosine of 0, is 1. The derivative at 0 is 0. -1, 0, 1, and the pattern continues. When we simplify this expression, we see that all of the odd degree terms have 0 coefficients, leaving us with only the even degree terms in this series, and with the now familiar alternating signs, giving us our familiar expression for cosine of x. And so, it seems clear that we ought to be able to apply this method to other functions as well. Let us do so with another function that is at least reasonably simple. What would a very simple function be? Well, let's take a polynomial. In this case, x cubed plus 2x squared minus x plus 5. I know that we can differentiate this with ease. If we evaluate this function at 0, we obtain the first term in the series, namely 5. If we take the first derivative of this function, what do we get? Well, 3x squared plus 4x minus 1. Evaluating this at 0 gives us what? Well, that gives us -1. Therefore, the next term in the series expansion is -1 times x. Continuing, if we take the second derivative of this function, we will obtain 6x plus 4. Evaluating this at 0 gives us simply 4. Therefore, the next term in the Taylor series is 1/2 factorial times 4 times x squared. The third derivative of this function is very simple. It is exactly 6, independent of where we evaluate it. Therefore, the next term in the Taylor series is 1/3 factorial times 6 times x cubed. What happens when we take higher and higher derivatives? Well, the derivative of a constant is 0. Thus, all of the higher derivatives vanish, and all further terms in the Taylor series evaluate to 0. So we can drop them out without consequence. Rewriting, using a bit of simplification, gives us the Taylor series for this function as 5 minus x plus 2x squared plus x cubed. Let us take a look at our work. Do we believe what we have done? Well, of course, this is exactly the same function that we started off with. We've merely written the terms in ascending order of degree. This seems like a trivial example, but it is actually very crucial. You must remember that polynomials have themselves as the Taylor series. Polynomials have polynomial Taylor series. This is going to connect to some very deep properties concerning polynomial approximation. Our strategy, therefore, for working with functions is to think of Taylor expansion not as a function itself, but as something like an operator, as something that takes as its input a function and returns as its output something that is in the form of a long polynomial, or better, a series. Why do we want to do this? Well, series, thought of as long polynomials, are very simple to work with, whereas some functions can be obtuse, very difficult, maybe even unknown in a specific form. Taylor expansion helps us to convert such objects into an easier to work with form. Indeed, Some functions really can't be defined well except as a Taylor series. Here's an example that I'll bet you've never seen before, though it's a famous function. This is the Bessel function, J0, that is most easily defined in terms of its Taylor series as the sum, k goes from 0 to infinity, -1 to the k, times x to the 2k over 2 to the 2k times k factorial quantity squared. That's a bit of a mouthful. We could write that out, and we would get something that doesn't look too bad. There are a lot of complexities in the coefficients there. How might we understand this function? Well, let's see. The general form of it is reminiscent of the expression for cosine that we have derived, in that it has alternating signs and only even terms. But notice that the denominator of the coefficients is growing very rapidly, much more rapidly than k factorial or even 2k quantity factorial. We might therefore anticipate that the graph of this function looks something like a cosine wave, but with a decreasing amplitude as a function of x. Have you ever seen such a function before? Maybe you have. If you've ever taken a chain or rope and rotated it about a vertical axis, if it winds up in equilibrium, the shape that you will get is related to this Bessel function. If you drop a pebble in some water in a round tank or an open pond, the rippling effect of the waves is going to be very closely related to such a Bessel function. These are not too unusual, even in everyday occurrences. In fact, for a chain or a rope that is rotated in equilibrium, we can describe the displacement away from the vertical axis, r, as follows. This r is proportional to the Bessel function, J0, evaluated at 2 omega over the square root of g times the square root of x. Here, omega is the angular frequency, or how fast you're spinning that rope. G is a gravitation constant, and x, most importantly, is the distance not from the top of the rope, but from the bottom of the rope. Now, you don't need to remember this formula. You don't need to know how it's derived. What we are going to look at is what happens when we substitute these values into our Taylor series for the Bessel function. One of the things that we can conclude from this Taylor series is that if x is reasonably small, if you're near the bottom of the rope, small enough that we can ignore some of the quadratic and higher order terms, then what's left over looks like a linear expression in x. R is proportional to 1 minus omega squared over g times x. That tells you something about the slope at the end of the rope, namely that this free end is swinging with a slope that is proportional not to omega, the angular frequency, but to omega squared. The faster you spin it, the more the slope changes. And we can say exactly what rate that change is. It's quadratic. You can try this at home with a piece of heavy rope or chain.
This lesson has given us a new definition, that of Taylor series, as well as a new perspective, the idea that expanding out a function into a long polynomial or series is advantageous. Next time, we'll consider the question of how one can effectively compute these Taylor series.